Hello, and welcome to the first part of the first lecture on this course on chemical process design. We're going to start this course by examining three key sets of documents that chemical engineers use to communicate with not only one another, but also with other engineering disciplines. The importance of clear, concise and accurate communication cannot be overstated during the design process and during plant operations. It can, at times, literally be a matter of life or death. The first part of this lecture examines the anatomy of the process flow diagram, or PFD. I have no doubt that you'll already be familiar with these documents, but I'd like to formalise what you know and give you enough information such that you can draw these diagrams to the necessary standard. Firstly, we'll look at how the drawing of the process is put together and what information should be present. Then we'll look at how composition and flow data is displayed and the level of detail that's required. Finally, we'll have a look at other pieces of information that should be present on the PFD. So, when one thinks of a process flow diagram, or PFD, what you're seeing is the process roadmap. It gives you the clear, unambiguous, uncluttered view of how the process is put together. There's enough detail to understand how the process runs at steady state, but there's not so much detail that that understanding gets lost in a morass of information. So, when one looks at the PFD, you can clearly see the arrangement of the process equipment. You can clearly see some data pertaining to stream flow and stream composition, and you can also clearly see some data that pertains to process operating conditions. The PFD is an essential document. It is used by many different disciplines. It can be used by the design team to further evolve the design and to be passed on to specialist design groups, for example piping layout groups. It can be used as a training document, for example during operations, for training operations personnel and for creating operating instructions for the plant. Furthermore, it can be used for training operators, and it can also be used for comparing operating performance with design performance. Sometimes these two things can be rather different. So, in order for many different people, sometimes from many different disciplines, to understand it, the PFD has to conform to strict universal standards in terms of symbol set and in terms of layout. I've put on Moodle for you an extra resource which discusses how PFDs can be used as a communication tool. It's an article written by the American Institute of Chemical Engineers back in 2012, and it's called Using Process Flowsheets as Communications Tool. Please do have a read through that because it serves to reinforce what I'm going to be saying in this part of this lecture. The best way to explain the process flow diagram is to actually look at one and take it apart piece by piece. So here on my whiteboard I've put a candidate process flow diagram that we're going to dissect. The first thing we're going to look at is the way in which the process is represented. So I've put a red box around the drawing of the process. Let's zoom in on that and look at some specific details. Now, when we look at this, we see a snapshot of the steady state process. This is really important. This is not the startup process or the shutdown process. This is what is happening at the designed steady state. It includes every item of capital equipment, however, that you will see on the plant. So it includes startup, shutdown and any duplicate equipment as well. Now, if you take those two first sentences, it looks like a contradiction in terms. However, it's not, because the snapshot of the steady state process, which is reflected in the stream table data that we'll discuss in a few slides' time, has those startup and shutdown items basically having zero flow, if that is the relevant condition for them. So the snapshot of the steady state process can include those items of equipment that aren't used at the steady state, but they're designated as being shown as not being used for the steady state. Now, the reason why all equipment is included is because the process flow diagram can be a very useful document to aid, for example, accounting. When you're doing a design and you're looking at the design finance, you might look at through your list of capital equipment that you've costed up, compare that to what is illustrated on your process flow diagram and make sure that the two things are the same. If your unsteady state, your startup and your shutdown equipment wasn't included on your process flow diagram, it would lose that utility. Furthermore, when it comes to training, it would also be missing a potentially substantial amount of equipment. Now, a very important point to note when you're drawing a process flow diagram for the first time, especially if it's derived from a process simulation, is that there is a key difference between the symbols that you see on a process simulation and the mechanical equipment that you draw on your process flow sheet. When you're doing a process simulation, for example in Unisim or in HYSYS, you'll have mathematical operations as shown on the flow sheet alongside models of capital equipment. So for example you might include recycles or mixers just to bring, for example, two gas streams together. The important thing to always ask yourself is the following question. Is what I am drawing on the process flow diagram an item of capital equipment? If the answer is yes, it should be shown. If the answer is no, it shouldn't. Mixers are a particular point of confusion. It is usual within Unisim, if you want to bring two streams together, to show a mixer block. For two gas streams, this is just simply the addition of physical properties, and very often, if you were designing a unit to accept two gas streams, you just have two entry flanges on your item of equipment. There'd be no need to have a physical item of equipment to mix those streams together. The turbulent flow in each of the gas streams would be perfectly sufficient to do that in its own right. If, however, you had two liquid phases that required thorough mixing, then you would need to design a piece of mixing equipment, and that is a specialist item of capital equipment, and that should be shown on your flow sheet. So the word of caution here is don't blindly copy what you have on your process simulation onto your process flow diagram. Make sure that you appraise what it is gets included and what it is that gets omitted. Now, when it comes to showing symbols like I've shown on the whiteboard here, there are standard symbol sets you should use. In your notes, I've put a list of the commonly encountered symbols for the British standard, BS 1553. You should be aware, however, that there are a number of different standards, specifically those that are used in the US versus the UK. Now, let's take apart some of the information that is illustrated on this diagram. I've highlighted a symbol, and it's a little diamond symbol, and that is a stream number. If you look at the process flow diagram in depth, every stream is given a number. There's a number of ways in which you can do this. You can put a little number with a cardigan adjacent to a stream. My preferred way is have a little diamond, such as shown here, with a stream coming in and a stream going out. It makes it very unambiguous which stream that number actually relates to. Moreover, every vessel on the process flow diagram has a unique code. For example, the reactor here is R1-100. The separation column is C1-130. So there's a letter prefix, R for reactor, P for pump, C for column, T for tank, V for vessel, E for heat exchanger. And then there's a two-number set. The first number sometimes pertains to the process area. It is usual to divide a plant into a number of distinct areas. And then the second number is actually the unit code. Then, if we further look at the process flow diagram, we'll see that where streams enter and streams leave, they are flagged with a descriptive name. If these streams are continued onto a different process flow diagram, there's data here to show you where to find the continuation of that stream. This is done by a grid referencing system, which we'll introduce in a minute or two. Okay, what else can we see? Well, if we take a broad overview of how this segment of process is drawn, you'll see that the line weight and line colour differs. Now, it may not always be practical to have line colour. Very often process flow diagrams on plant are going to be shown in black and white, especially if it's an old piece of plant with paper-based diagrams. But the line weight is very important. A bolder, thicker line shows the key process flow. So it should be very obvious when one looks at the diagram where the key material flow actually goes. And one way you can do this is by highlighting that line, just by making it more visually attractive, make it stand out. If colour is an amenable thing to do, then you can layer additional information which gives visual representations of what the streams may contain. The other thing that's very important in process flow diagrams is to clearly demarcate if there are differences in modes of operation. The example that I've put on the whiteboard here has a piece of plant that is in batch operation and a piece of plant that's in continuous operation. And again, because of the nature of the PFD, specifically when it's used as a communication tool, you should be very, very clear about which parts of the process are continuous and which parts of the process are batch. Now, very often you will find heat integration on pieces of plant equipment. It's a very sensible way to save energy and to reduce your running costs. When it comes to clearly showing heat integration on a process flow diagram, you have to think about the clearest and most unambiguous way to illustrate it. So I'm going to give you two examples of the way it can be done. Each example concerns the same distillation column, and what we're doing is that we're having heat integration between the residue stream and the feed stream. This is quite a common process integration, and it enables a little bit of feed preheat to be recovered from an otherwise hot residue stream. So if your feed preheater is taking residue from the same column and the units are in close proximity to one another, then the clearest way to illustrate the heat integration is as I've shown on the board here. Have the heat exchanger with the stream, the process stream, coming in on the service side. It's very, very clear, it's unambiguous. However, if you're heat integrating across several different process flow diagrams, for example, if we were using the residue not from this column, but from another column in a different part of the process, illustrating heat integration in this manner can be unclear because you have streams leaving a process flow diagram, performing one operation on a different process flow diagram before going back again. So there's an alternative I'll introduce with caveats, and it would be this. The two heat exchangers I've highlighted in red are the same heat exchanger, the same one as I've highlighted in blue on the other diagram. What I'm doing is showing how the shell side is integrated and how the tube side is integrated. So on the left hand side of the image, the feed goes through the tube side, and you can see the process stream is integrated on the shell side. On the right hand side, you can see the reverse. Now, this should only really be considered if the subject of heat integration spans several different PFDs. It's potentially very ambiguous. If you're counting capital items and you're looking against a balance sheet, you are very likely to count this heat exchanger twice in error. So if this scheme is going to be used, it should be accompanied by a very clear written note by both instances of the same heat exchanger, clearly stating concisely that this is showing a tube side and a shell side of the same unit. So use this with caution and only if it adds clarity to what you're doing. Right, let's zoom back out and look at our process flow diagram again. Highlighted in red, I have shown a data table. Now this data table gives you all the operating conditions for the stream, so let's have a look at that in a little more detail. When we think about stream tables, one can do one of two things. You can either incorporate them on the process flow diagram, if there's sufficient space to do so, or as a separate document that is appended to your set of process flow diagrams. The rule of thumb here is do whatever is clearest and most unambiguous. If incorporation onto the process flow diagram means shrinking the stream tables to an almost unreadable size, don't do it. Let's have a look what's shown on the stream tables. So for continuous processes, you first of all show both molar and mass flows of each stream. It's very important to include both. The molar flows can be important when you're checking, for example, reaction products and reaction extents. The mass flows, however, are vital when it comes to checking the mass balance. I've highlighted in red here the inlets and outlets of a distillation column to illustrate this point. The inlet, stream 1-6, your high pressure acid feed, is 100 kilograms per hour. If we look at the two outlets, the distillate and the residue, they sum to 100 kilograms an hour, so therefore we know the mass balance is obeyed. Highlighted in purple is a flash separation unit, and the same applies here. The inlet is 53.3 kilograms per hour, and we can see summing the two outlets, it comes to the same thing. So it gives a very easy way to check a mass balance very, very quickly. Now, if we've got batch and continuous processes side by side, we don't show a time average flow rate for batch processes. What we do is we show the total mass of material that's being moved and the given time that it's being moved in. So, for example, we see that 800 kilos of material is being shifted in half an hour into our reactor. From that, we can gauge what the pump size and line size needs to be, because it's far more accurate to look at that 800 kilos in half an hour than it would be some representative flow rate. Furthermore, we can then use this to inform how we would design, for example, batch interlocking, and we'll talk more about batch interlocking in a future lecture. Other information. The bulk of the table is taken over to composition information, typically given in mole percent or mole fraction. I've illustrated in mole fraction here, but sometimes you can use mass fraction. Again, the general rule of thumb is if you've got a chemical species with a defined molecular weight, formaldehyde, acetic acid, acetaldehyde, then use mole fraction. If, however, you've got a mixture of species that can be variable in composition in its own right, naphtha, kerosene, jet fuel, coal, paper, use a weight fraction. It's far more easy, therefore, to convey that compositional information. If we look at the top of the table, we'll see that each stream is clearly referenced by the stream number that appears on the process flow diagram and a short, unique descriptive name. It's short because there's not much space, it's unique because we want to be easily referenceable, and it's descriptive because we want to show the reader what it is that stream mostly comprises of. For example, enriched air, or hot acid, or volatiles. The final piece of information that we can see is at the base of the table, and here we can see pressure and temperature data given in consistent units for every single stream. Now, depending on the process, sometimes it can be relevant to put in other data such as mass fraction or density or viscosity or solids fraction or vapor fraction. I've omitted those from this particular table because they're not pertinent. If we look at the way the table's presented, we need to note a few things. First of all, look at how many significant figures are shown. I've used 2 significant figures for the composition data, so I wouldn't expect any more than that, maybe 3. If we look at the stream flows, the same applies, maybe 100.0 kilograms per hour, but if we're dealing with higher stream flow rates, then we might just say, well, this is 3,210, no 0.0, because that becomes almost meaningless information. So think about the number of significant figures that you show, think about the certainty with which you know the data, think about what is the most clear way of illustrating. No more than 2 to 3 significant figures, please. If you've got a long stream table, it's very easy, especially if all your labels for compositions are on the left-hand side, for your eye to jump a row inadvertently when you're trying to figure out what weight fraction or mass fraction or mole fraction that you're actually looking at. So sometimes sequential shading, like I've shown here, can be a very useful visual aid. Okay, so those are stream tables. Let's see what else we can see on our process flow diagram. I've highlighted here on the whiteboard some bits of ancillary information. There's a patch of information at the top, there's a border, and there's a box at the bottom right hand side. So let's have a look at what information's there. Firstly, at the top of the table there is a catalogue of each of the major units shown on the PFD. It includes its tag number and a short descriptive name. So we can see that we've got a 1, 2, 3, 4, 5, 6, 7, 8, 9 units shown on this process flow diagram, and that we can see a brief description of each of their operations. And this can be a very useful counterpoint such that we can quickly understand what's going on the process flow diagram. What we can also see is a border. Now, a few minutes ago I said that if streams leave and reappear on different PFDs, it's very useful to tell the reader where they appear on a new PFD. And so having a border that's grid referenceable, letters along the horizontal, numbers down the vertical, allow you to give coordinates of where you will find a stream appearing. Also, they can be useful in discussions. If you've got 5 pumps on a process flow diagram, then it might not be easy to locate P-1-152. But if you can say that it's at reference A7, then the readers can easily find it. Finally, and almost most importantly, there's some information at the bottom here. This is about what version the drawing is, when it was drawn, what it pertains to, who drew it, and so on and so forth. I've given a list of information that should appear there, but the most important one is at the bottom, revision number. When you are designing a piece of plant equipment, you will go through many iterations of design. you'll go through many iterations of process flow diagram and even more iterations of the document we're going to talk about next, the piping and instrumentation diagram. When discussing these documents with other engineers, it is vital that you can all check that you're working from the same information, which is why a revision number is so important. Different revisions can at first sight look very similar, and it can be very easy to inadvertently start talking at cross purposes if you haven't got a solid way of checking that you're all working from the same information. So please include a revision number. So let's summarise with a few key points. The process flow diagram, or PFD, is a key chemical engineering document. It illustrates the process with a standard symbol set. You've got lines and you've got vessels with tag numbers. You've got boundaries showing the border between batch and continuous processes, if that's relevant. And the key thing here is it's got to be clear and easy to read, so pay close attention to how neatly you draw these diagrams. Stream data is included in stream tables. It can be put onto the PFD if it is clear to do so. If it is not going to be clear, if the stream data information is just simply too big, include it on a different document. If one looks at the stream tables, you've got mass and molar flow information. You've got compositions, either in mole fraction or mole percent, or weight fraction or weight percent, depending on the nature of the components. And you've got information pertaining to pressure and temperature. When you look at the drawing page for a PFD, you've got a grid referencing system such that you can easily identify the location of items of equipment or continuation flows. You've also got essential drawing information such as the author, the date, what the process is, and most importantly, revision number.